So those equations are exactly the same as they are in seismic. It's just that the relative importance of the traveling wave versus dispersive is entirely turned around. But the fact that they're mathematically the same led a lot of seismologists to try to understand what the EM was in terms of the jargon that they know and their lexicon. And seismologists see up and down going plane waves, they see reflections, they see refractions, and at some level, you can make that correspondence, but it doesn't take you very far. On the other hand, if you just simply accept the EM equations, forward modeling, and look at them, then you can, by seeing how the fields propagate in time, you can get a sense of what's going on. Here also is where it shows the importance of establishing a physical understanding first by looking at the time domain results and then going to the frequency. Even for us, when we looked at the frequency wave results, they're confusing. You just can't quite figure out exactly what's going on. On the other hand, when you look at the time domain results, you realize like, oh, that is absolutely so simple. Okay, so let's do it. We're going to talk about application areas. We're going to take a step back and look at the whole CSEM problem, not necessarily with respect to hydrocarbon de-risking, but all kinds of things. If you ask where can it be, oil and gas certainly, but there's massive sulfides on the ocean floor. This is actually, you're going to hear a lot more about this in the next few years. Japanese are already starting to mine the ocean floor for these massive sulfides. There's methane hydrates, talk about that, tectonic studies, unexploded ordnance offshore, and there's groundwater, offshore groundwater connecting to onshore groundwater. So there's a lot of reasons to do electromagnetic surveys in environments that have substantial amounts of water. So always the very first thing we ask is, okay, what's the physical property? What is the electrical conductivity or electrical resistivity that we're dealing with? And if we're looking at seawater, for instance, then we find it's very conductive. 3 siemens per meter, or just a fraction of an ohm meter. Fresh water is hundreds to thousands of ohm meters. Sediments, 1 to 5 ohm meter. Hydrocarbons are about 100. Hydrates, gas hydrates, 2,000 ohm meters, so very resistive. Massive sulfides are really low resistivity, maybe 0.1, 0.01 ohm meters.
In mining studies, what you call,
pardon me?
In mining studies, you call conductive sediment about 100 ohm meters, and resistivity is about 500 meters. And then offshore sediment, because of the water formation, sediment resistivity is about 1 to 5 ohm meters.
Mm-hmm. So in general, seawater is very low resistivity. Freshwater is very high. Sediment, relatively low resistivity. Hydrocarbons are mid-range. But the thing that's important here is distinguishing, hydrocarbons from some combination of freshwater and seawater, right? So some kind of brine. And you can see that could be quite different. And then hydrates and massive sulfides, those are both sort of nearer surface things. So, but that's the big ticket breakdown for these. When you're have a hydrocarbon play, you've got a reservoir here with some thickness. It's buried at some depth. And the very first thing that you think of, like, okay, it's a resistor. So, resistor, you're thinking some kind of galvanic type of circuit. So you're thinking DC resistivity. You're not thinking, EM induction, because this is transparent to that. So I think maybe that's, here is, I think, perhaps one of the kind of takeaway points of a reason for attending a course like this if you don't know anything about electromagnetics, is that even at this stage, from all the stuff that we talked about, you realize if somebody gave you something like that, they said, well, of all of these different kinds of EM techniques, which would you use? I mean, you certainly say, okay, we need some kind of a grounded source technique. So already you're throwing out all of these big loop inductive sources and stuff like that. So we need, first of all, find a resistor, grounded source. The other thing is we have a deep target. So we need somehow a long offset with our array, and that array could be the transmitter and receiver. And we've talked about the depth of penetration that you can see in this. And that rule of thirds is pretty good. So if you just have that rule, and you say, okay, my reservoir is 2 kilometers depth, then you're going to need 6 kilometers between your transmitter and your receiver. So if you're going to do it on a cable, you need 6 kilometers of cable. So just a few basic elements and this kind of idea gives you a huge amount of information, right? Okay, I've got a galvanic system. I've got to have a long offset. So if I'm going to tow a cable, if it's 2 kilometers depth, I need 6 kilometers of cable. I mean, those are really, really fundamental, important things. If you have a conductive target, like a massive sulfide, then now we could do either. Like we could have a towed system like this. We could have grounded dipole, or we could have an inductive source, right? Because now we could get induced currents in here. So both of those are possible. What do we have for transmitters? For grounded sources, one of the most commonly used is the Scripps source. It's basically a current bipole of length DL and a current I. So the moment of this is given by the product of I times the length. And that can be towed. So there's a big generator on board, putting hooking up to this grounded wire. So the current is going to come out of this end and go back into the other end. So it's just the same as when we talked before about having a dipole in a medium. So you got a current source, steady state currents kind of go like that.
Is it supposed to go very close to the sea bottom or not?
The closer that you can get to the sea bottom, the better you are. You always want to be close to that target.
Practical? What's the usual distance?
Yeah, usual.
DMGS flies that stuff in 30 meters.
30 meters.
Above the
Sea bottom.
yeah.
Yeah, I'm sure there's places where topography is rougher. And, usually you do not want to drag that stuff into the side of something.
In canyon, for example, they pass through. They don't follow the canyon.
Oh yeah.
They pass.
Well, if you're towing 6 kilometers of cable,
Yeah.
it's pretty challenging. So that's a grounded source. You could also have an inductive source. And there's a couple of universities, one in Japan, Osaka University, and then also Geomar have systems that look like this. So now, here's a loop of wire, just strong over here, and it's got a certain area. You pump a current through that, you got a dipole moment, and you drag that over top. It'll induce currents into something.
What is these dimensions of this square loop?
Probably like 10 meters or
10 meters.
something. How big is the?
It's I think about 3 meters.
Oh, is that in radius or diameter?
Like the length of the, yeah, so the one arm, like the one.
Out here,
width,
3 meters.
Yeah, about 3 meters by 3 meters.
Yeah, so 6 meters. No, 3 meters.
3 meter diameter.
So it's it's a rectangular. Sure, it's a
Yes.
3
Inside.
by 3.
Oh, okay. Oh, so I was.
I'm not sure if that's the radius.
No,
Nine square meters.
Yes. Oh, area.
Okay. I said 10. Okay. There we go. It's small. It's not 100 meters or anything like that. It's those transmitters. Okay. The important thing is it's a dipole here, so there's a geometric decay of 1 over r cubed, and anything that's in the frequency domain has got an attenuation, that's given by the CSEM App. That's a transmitter. What about receiver? Well, receivers, E and B field receivers, so electric, magnetic, and they can be in various places. You could have E field sensors on the streamed cable like this. So you've got potential electrodes out there, and they're measuring electric fields. You could also have ocean bottom nodes. They could measure all 3 components of the electric field, which is now becoming more common, as well as components of the magnetic field. And here's what one of the scripts institutes like. So it's basically for electric field measurements. There's plastic tubes out there to measure the potential difference between here and the other end, and same with EY. And then the magnetic field coils are sitting inside here. The receivers for here can also be magnetometers or coils and sitting up inside this housing. In fact, I guess that's the 3 coils there. Well, yeah. So let's take a look at what the effect, what the responses would be from a typical ocean, and then we'll also put in a layer of hydrocarbons at depth and get what we call a kind of a canonical model. I'm going to use that to get some idea about what the signals are and to really understand them. So the first is that we've got an ocean that looks like this. So there's an air layer, and then there's a kilometer of ocean water, and then from 1,000 meters down, it's just ocean sediment. So this is going to be 1 ohm meter here, and this is about 0.25 ohm meters. So that's our basic background model. And if we measure the electric fields as we go away from here, so imagine you got your dipole here, and now it's just like your DC survey. You're measuring potentials here, here, here. And so measure those electric fields as we go in offset. So this is distance away from the transmitter. The electric field just drops down like this. Kind of nice, smooth decay. And then it does something that's kind of unusual. Because there's kink in it, and then it falls off at a different rate. So that's kind of interesting. Like there's definitely something going on here that is causing that. And we'll come back to that, because there's actually some different kind of physics or waves that are coming in. But now let's put in a hydrocarbon layer at about 2 kilometers depth. So we'll put in a reservoir, and we're going to take a look at what happens here. We're going to put a particular frequency in here. So we've got an electric dipole. We're not going to just put a square wave in and shut up. We're actually going to put in a harmonic signal. Okay? So we're going to put in we use a 0.5 hertz, and we look at that signal, and it looks very different. It kind of comes like this. So this was one of the reasons that people started to get pretty excited about this, because the difference between no hydrocarbon layer and a hydrocarbon layer was very, very significant. So that was a strong motivation for trying to do something. Within this example, so now you can start to see kind of what happens. Everything is going to kind of depend upon the charges that are being built up on this resistive layer, and that's going to give rise to those electric fields. We can think about things in the frequency domain. I can show you some plots, but everything is made much more understandable if you look at what is going to happen in the time domain. And in the time domain, we can actually think about waves that are propagating as a function of time. Because what's going to happen is, we could set this source off, so we have constant current, turn it off, right? And then there's going to be energy that's going to propagate out. Because we've got a medium here that has got a number of different layers to it, there's quite a few ways that energy could travel. And the seismologist, this is probably a diagram that you kind of really affiliate with, right? So we've got a source here. We could get energy that's propagating in the ocean. So the receiver over here. Energy that propagates in the ocean. We could get energy that propagates at the surface of in the sediment. We could get energy that propagates maybe in the hydrocarbon, and also maybe something that goes up into the air and then across. So that's a set of ray diagrams that seismologists are like, okay, that sounds good. There's a question at this point, like, okay, which fields should we look at? Because we've got quite a few. And then there's also something called the Poynting vector. How many people have heard of a Poynting vector? Good, okay. So if we look at the cross product of an electric and magnetic field, then that gives us an energy density that is propagated. The direction of that is which way the energy is. So what I now want to show you is a movie. And say this is one that Soggy put together. We obtained a code that was written by Dieter Mueller. By Dieter.
We'll send him the recording.
It's written by Dieter. Anyway, he wrote a very nice Python forward modeling code that allows you to simulate data with a 1D Earth with different kinds of sources. There's also the potential for anisotropy to be included in the model. And it's very versatile. And Soggy hooked this up for the C4EM problem. And now I'm going to show you the movie. So what we're going to see, first of all, is the electric field. Okay, so remember, we're starting with a horizontal source. So there's a current that's going like this, right? And so if we look at the currents that are going to come out and the direction of the electric field, if we're kind of in line, this is the x direction, and the currents are kind of go like this. So the fields that are kind of along this line are both in the sort of x and z direction. So we're going to measure just the X components of the field because we're dragging this this receiver set, so it's in a line parallel to the transmitter, and we're going to look at the EX component. It starts off like this. The current was flowing in this little wire in our dipole and then has been turned off. So this is about a millisecond after turn off. And what you're seeing here is the high values of the electric field. So they're actually still confined pretty close to where the transmitter is. We'll expect those fields to propagate out with time. And what I want you to watch for, I'm going to play the whole movie. We'll play it a couple of times. But I want you to watch how this current or these fields kind of propagate out and where they go. So first of all, let's just do something here. So here's our current source, yes? And this is water. So this is sigma, well, yeah, sigma. No, let's do both. And here is sediments. Okay. So we're going to have energy that propagates out. And I first want you to tell me, as the energy propagates in this medium and in this medium, in which medium it's going to go faster. In here? And on what basis are you judging that?
The conductive one. Not conductive.
In here? Our back row? In which medium it goes faster, and why do you make that decision? Well, there's only two choices. It's either the upper or the lower. Okay, how many people say it's going to go faster in the conductive medium? How many people say it's going to go faster in the resistive medium? So we've got 3 for resistor. And anybody for conductor?
I changed my mind.
You changed your mind. Okay, and why did you change your mind?
I got the students help.
Good. I don't know. There's never a substitute for experience. So, you know, age has its benefits. Okay.
It may have something to do about the frequency. I don't know.
Well, there's no frequency in here. This is a time domain.
Just time.
So the energy it's just like a seismic wave, right? So okay, so I've got a seismic gauge. So this is V is equal to 1,000 meters per second. And this is V is equal to 2,000 meters per second. And I'm going to put a source off here, which is going to go faster. Good choice. Yeah, so maybe this one, right? Okay. this question is not so much harder. So in resistive, okay? Why?
If we continue with this seismic waves to electromagnetic wave
Perfect. Love it.
comparison,
Yeah.
in seismic waves, the more rigid, the more stiff is the medium, the faster the waves propagates. So if you think that the more resistive is analogous to a more stiff rock, that's how
There's a term.
That's a little bit of a stretch for me. We actually did some stuff earlier that will tell you exactly.
we were just following your
Yeah. Oh, good.
Isn't there a term called electrical impedance? Is it
Yeah.
similar to acoustic impedance? Is it? I don't know. I'm remembering the high school.
Yeah.
I remember about the electrical impedance.
Yeah, the electrical impedance is, for EM, is like E upon H. So it's a ratio of an electric to the magnetic.
Oh,
So it's a bit different than seismic
nothing to
impedance,
do.
so electric impedance is working with field, seismic impedance is working with physical properties. Okay?
Diffusion distance.
Perfect. Yes. Whoa. You can stand up. Sit down. Oh. Okay. At the end. Okay. So at 3 o'clock, you're all going to be allowed to touch Cristiano just for a second. Just touch his hand, and you'll be okay.
I'll touch him just up here.
Okay. So remember the diffusion distance. It's like 1,200 or 1,300. I think it's root rho T. Okay, so the higher the resistivity, the faster the waves diffuse through. So at a particular time, the waves in here should have gone much faster than here. So if we would expect, as we're going through here, actually we could kind of figure this out. Let's try to do this. So we've got stuff coming out here, and now we've got a wave that is propagating out faster here. So a little bit later, the wave front might be out here in this medium and only out here. So at a particular time, maybe we're kind of expecting that, right? Okay. Now, suppose that we have a hydrocarbon layer. Okay? So now you can use all your seismic intuition here. So we've got a wave front that's coming out here, and we've got another wave front that's coming out here, right? So this is propagating out faster in this medium. So this is the second. Now, what's going to happen as a wave impinges on this guy? So here was rho equal 1, and this is rho equal to 100.
propagating downwards.
When it propagates in, as it's going in here, okay? Now it's in a region. Yeah, so if it's perpendicular down here, then it will, but there will be stuff that's coming in at an angle. And so you might think, that some is going to propagate down through, and you might also think that some is somehow going to get channeled in. So some portion is going to get channeled. Okay, that's okay. Now what's going to happen to this? Anything that gets in here?
Propagate much faster.
Perfect. So after a little time, okay, once this hits, there might be energy that propagates in. So at this particular time, we might actually expect it to be that the energy would be looking like that. Okay? Okay, so we might expect now a picture like that. We've got one more thing. We also have this up here. So this is air. So this is rho is equal to, let's say, 10 to the 7. Comes up.
Much more faster.
Yeah, this is going to go zipping along, right? So at some particular time, if you're far enough away, the energy has to diffuse up here. But the moment that it gets up here, then it goes over there, right? So now imagine that you're sitting on the ocean bottom. So here's your transmitter, and now we're sitting kind of right here. Then, if we're initially what we're going to expect is energy, a large amount of energy. So it might come in like this, and then so I'm trying to get back to the diagram that we had that was kind of coming in like this, and then well, that's bigger. Let me try it again. So the diagram that we had showed that the energy was like this. And remember, then there was that kind of cake there. So let's try to understand what might be happening. If we're really close to the transmitter, we're going to see energy that comes in, first of all from the sediments, and then from the ocean. If we get out a little bit farther, actually the first arrival might be energy that's down here and has slipped out through here. And if we're out a little bit farther yet, it takes a long time, and depending on the thickness of the ocean, for the energy to get up here. But once it gets up, it's like this. So here's where that bifurcation comes in. Up until this point here, we've got energies that are coming in through these various ray paths. At this particular point here, you're going to have a critical point where the energy goes up and then kind of goes over. So the first arrival is actually going to be what's called the air wave. So this formula, E is equal to 1300, plays a real critical role. Okay, so now let's.
I have a question. So,
Yeah.
So you're saying this kind of signature in your energy only happens in CSEM? Like, so you see this kind of basically that critical point, and then after that you have like energy kind of stay at an almost constant value.
Well, it doesn't decay as rapidly.
So what's like?
Well, because any energy that gets in through the air only suffers geometric attenuation. So it's not suffering any other attenuation. So that means it can propagate a long ways out this way without losing a lot of energy. Of course, that wave then has to, so the wave that propagates out here is still putting energy into the ground like that, and it's the receiver that's sitting out here that's gradually measuring it. But from the point of view of of energy, without this air wave, the energy is coming in through these various ray paths, and the total energy is.
So you're saying after that point, what you measure is actually their air wave?
Well, a large part, a contribution of that is to the air wave. And
So-
that's a bit higher than that's not attenuating as rapidly as energy that's moving through
So
here.
So if you have the same system, but like the experiment is conducted on land, will you get the same kind of response?
There is an air wave that,
So
for land surveys, but it usually goes by so quickly that you're not really affected. But the physics is there. If I set off something in here and I'm sitting up in here, then there's energy that propagates out this way. It's basically at the speed of light, and we don't have to consider that as far as being a major energy contribution. So it's yeah.
So for the EM system, you normally ignore any kind of measurement beyond that point. Is that right?
Well, we
No.
usually don't measure.
We can't measure early enough. If we were able to measure, at nanoseconds or femtoseconds early, then we'd see that.
GPR.
GPR.
Yeah, GPR.
Okay, yeah, because actually, that's what I exactly see in the signal that we do this kind of ground. The
Yeah.
ER, that's basically what we measure.
Yeah. So
So I just,
all of this that stuff is in what's called the displacement curve term, the d/t, which we acts out, and we said we're doing quasi-static. Right. So everything that we've been doing up to this point is like quasi-static. So we're not looking at these either super high frequencies or really extremely early times. But when we do the GPR, then we'll have the full Maxwell's equations, then we actually have, there will be an air wave that comes. In fact, the air wave then in the GPR, the air wave is actually a really important thing. And we have made the mistake of confusing air waves with substructure. You have a GPR survey, and you get energy that goes out, bounces off a fence, and then comes back to a receiver, and you think, oh, well, that's coming from underneath there, but it's not. But in everything that we've been doing up to this point, we're in the quasi-static regime. We're just simply not considering this, and as long as we're under reasonable Earths and under 100,000 hertz or something like that, it's a good approximation. Okay, so we've already got some idea about what might happen, and just as in any app, this is what you want to do. You want to kind of sketch things out, have an idea of what's there, and then try. Yeah.
Questions. The source there is like a dipole, this way.
Mm-hmm.
Yes. So it's natural that the wavefront. Can I call this a wavefront?
Sure.
Yes. It's natural that it's more stretched in the horizontal direction than in the vertical.
Yeah.
Yeah. So should it follow a specific shape, like an ellipse or rectangle or something? Because seismic waves in a homogeneous medium should be symmetrical. This should be spherical.
Oh, what yeah.
Radiation pattern.
Yeah. So when you did, for instance, in fact, you have an app that does an electric dipole in a wholespace and at different frequencies, and then you can see how the field lines change with that. Okay, so are you ready? Catch your breath. Oh. Okay, so right there, okay, so now you can see that it's really kind of moving out fast. Look at it. See, this is how fast it's moved out here, and there it's less, right? So it's moving faster in that more resistive medium. And now the energy has got all the way down to here, and you can start to see it's starting to propagate along. Up here, it hasn't got there yet. So far, we're just, in fact, we're almost exactly in this position right here. That's even better, right? So now you can really see. Do we need to turn the lights off, though? Oh, that's better. Thanks. So now you can really see how this is moving up this way. We've got lots of energy out here. And we're just, now look at this, we're just starting to get energy into that surface up here. Now you have to watch really fast because it happens. I'm not sure whether you're able to see this, but it just, it hit up here and then just streaked across. In this hydrocarbon layer, the energy has gone up into here. And there it is. And then it just disappears. Okay, so let's just play that again. That's perfect. There's one more thing I want to show here. So notice that the electric field in this layer is basically vertical. Okay, so the electric field is vertical. We've got a wire, so there could be currents. So there's magnetic fields that are going to be in the Y direction, that's into the board. And now when we look to see, okay, how is the energy propagating? That's really E times H. There's that cross product of E and H. So if E is going down, H is into the board, E cross H is horizontal. So that's what we'll look at. So here's, as I say, this whole thing, what did it take? 15 seconds to look at this movie. And you see this, you see things happening in the time domain, you see how the fields are changing, and then it's like, okay, why are people even discussing this? It's just so simple and obvious. But there's many papers that were written, lots of controversy because people couldn't really think about what the airwave was or when it came in. And it wasn't until there was a formative paper with a geophysicist by the name of Peter Weidel, who was a German theoretical geophysicist. And he wrote a wonderful paper that just kind of outlined all of this. And that was kind of the fundamental paper that was written. And then Dieter put together, his forward modeling, and then you kind of put everything together and got an answer. Okay. So now, that was how the fields are, but the energy actually propagates in a way that's dependent both upon the electric and the magnetic field. So that's why we're going to do this Poynting vector E cross B or E cross H. And we're going to see essentially the same plots, except that the vectors now are going to be in terms of how the energy is propagating. And again, what I want you to watch is look at the energy that's propagating in this particular layer down here, and you'll see what happens. So by the way, so the receivers, just to remind you, are all sitting on this interface. So the signal at any receiver is the composite of energy that's coming from all of these different waves. I mean, so it's just the same as in seismic, right? You're sitting at a single point, and you've got reflections from here, and you've got primary routes from there, and everything is kind of confused and summed up. The same is true here. So we've got to get the energy here. There is a first path of energy, but what you're really looking at is the sum of the energies that have come from all of these different, basically different rate paths. So now, if you look at these vectors, so you can see, okay, so so it's kind of like normal to that wavefront. So the energy is going up this way, down this way. It's here, the energy propagates along here, then there's some that's going down. Second. So energy is propagating here, but energy is also propagating up here, right? So it's kind of think about it. It's kind of like a head wave. It's kind of wave. It's a head wave. So it's traveling along here, but there's energy that's continually propagating up, right? So if you're sitting in here, you can think of kind of like direct waves that are coming, and then you got, a refractive, like a head wave that's coming in. And at this point, there's still nothing that's propagating down from the surface. That'll come.
What about the air wave?
So see here, now there's energy that's now propagating down from that surface. So as we're sitting here, we've got energy that's coming down. We've got energy that's going up.
And what's happening in this layer that the energy is like
But in
getting
here,
apart? Yeah, you have points. From this point to the right, and from this point to the left, it's an opposite behavior.
From 5,000.
yeah.
And if you play the move, this point just moves.
Right.
Why would the
Yeah.
The zero.
It's got to be the phase of the phase of the electric field.
You got a certain range in patterns, and it's distorted, and in time, it could be fairly complicated, and we're not 100% sure how to really explain that. I think at one point it's just you need to actually do a simulation, and that's
many iterations.
yeah. Can explain the first order.
First, well, and
More intuitive.
these first order times, right? Because this is fine in here, and then
What about the air wave?
yeah. What about it?
Air wave.
Yeah.
Where is it?
So-
So it's there. So it's
I
coming
thought-
up.
I thought it was much fastest.
Yeah.
From
Yeah. So you can see up here. So here's that wave, and then it's going to be propagating down. So there's energy that's going to go down into that medium. And so if you're sitting right here, you've got energy that's kind of coming up. You're still going to have energy that's coming down. And if you get far enough away, all the energy that's coming in through here is really attenuated, and it's small compared to what you're getting from the airway. That's why that curve kind of kinks over.
Tem note na câmera.
I'm not really sure how to explain that.
I think it is the.
It's a phase as it's going through.
It's just.
Yeah. Because it's still propagating, as e to the I omega t, right? So at some point, the electric, it's going in this direction, but the phase is positive, and then and then it goes to zero, and then it goes negative. That's why there's actually a zero in that crossing.
Yeah.
And if we could look at the speed with which that zero propagates along, that's the phase velocity of that particular wave. Yes, I'm pretty sure that's probably it. We'll go with that.
Should we get the lights?
Yeah, I guess you can get the lights. What? Fall asleep? No, not with a GeoSci course, surely. Okay, all right. So this is just kind of summary. So without that hydrocarbon layer, we got this black line. With the hydrocarbon layer, we get that. So they're the same up to a particular point, right? And then it takes a while for the energy to get into that hydrocarbon layer and then also get that energy back up. But at some point, it's actually really dominant. And on this case here, the air wave is not, it's still not observed as a big arrival, even up to 10 kilometers. But there are cases, and this is what happens if you put the hydrocarbon layer down deeper, if you change the depth of the ocean, then this air layer can actually come up as a really major event and be a first arrival. Okay. Yeah, I think we've kind of gone through all that. Yeah, just maybe one thing about this slide here. If you have DC resistivity, you have electric dipole, then things fall off as basically 1/r³. So you've got an app that you could actually do that. You could put a dipole in and see how the fields decay as you go away from that. You'll find it's 1/r³. In this ocean environment, we also have EM attenuation. And remember, that's e to the minus distance upon skin depth. So as you go to greater distances, depending on the skin depth, you've got this additional attenuation. So the largest signal that you're going to have from a DC resistivity experiment is when everything is really resistive, and then your electric field signal is just going to fall off 1/r³. The moment that you've got anything that is conductive, then it's going to decay. Which is also why once you get the energy into the hydrocarbon layer, it not only travels faster, it doesn't decay as quickly. So the skin depth in there is much longer. So that's why it's kind of like a guided way. You just get the energy in, it goes zipping along, doesn't decay, and then it comes back up. Yeah. I think. Oh, I just want to make a couple of comments now about the general CSEM problem. So there's a number of ways that you can think about acquiring data and doing something. So first of all, we could go ahead and just tow our system, right? That's fine. In that sense, what we're doing is just looking at what are called inline data. So we're looking at the EX fields in that particular direction. So that's what we've kind of been showing. But it could be a bit more general. You could imagine that you could populate the ocean floor with a whole bunch of EM nodes that could measure all components of the electric and all components of the magnetic field. So you could populate the seafloor, and then you could take a source and you could just drag it around. So this is the other way of working with things. You could have existing nodes and then just drag the source. If you think about what the fields are from a source, so if here's our dipole source, then in the horizontal plane, so the horizontal plane is this guy, then it looks like that. So the magnetic or the electric fields are kind of they're kind of parallel to the stratigraphy. So they're going like this, and that's so. If you have a receiver out here, you often refer to that as sort of being broadside. So the the current source is over there, and you're kind of broadside from it. And in that place, the fields are primarily horizontal and in like an X or Y direction. If you're in line here, then the fields that you obtain are primarily those that are going vertical and sort of inline. So you get this, and that's sort of called the inline. So the thing about the inline is that the fields that are most useful to you are the two electric fields, EX, EZ, and then BY. So that was the same kind of thing that we had before. And the electric field is actually going to cross the hydrocarbon boundary. Right? So the electric field is kind of going down and then up. So it's going to put charges on that top and the bottom boundary of that hydrocarbon. And that's why we saw that electric field go pointing vertically down. Right? On the broadside, the currents are kind of going parallel to the layer. Okay? And so there's no charge buildup on the layer, and you're effectively seeing, like the horizontal conductivity of this thing. So they sense things in different ways. Broadside induction dominates, and inline galvanic dominates. So the two things that we constantly been talking about. They will both be sensitive to the hydrocarbon layers, but the inline is going to be more effective. So when you've actually got currents that are going down and crossing that boundary, that gives a bigger signal. So in this particular example here, this is without the hydrocarbon layer, and that's with. And so you can see that's more than an order of magnitude difference in signal. On the other hand, if we look at the broadside, so now we're up here, then the background model looks like this. It's the dashed black line, and the canonical model, the one with the hydrocarbon layer, looks like this. So you still see it. You can still detect that hydrocarbon layer, but the amplitude of that, of with versus without, is much reduced. Which is why, in general, the best way to kind of work with these things, and the ideal way, is if you can just populate the whole ocean bottom with a lot of three-component mag, three-component E-field sensors, and then just drag sources back and forth so that you have long offset, short offset, and multiple transmitters. Then you've got good coverage. And that again comes back to the same thing as in seismic, right? You just need to have a lot of receivers, and you need to have a lot of sources that you kind of drag. So with that, I think this is a good time. We've got two apps that are connected with the CSEM, and I think you'll enjoy both of them, and they'll be very illustrative. So Sagi will come and take you through both of these guys. I want you to pay special attention to these apps because we have decided over the lunch hour that what we should do is to generate a few questions for you for the last day, in which you are forced to use invited. Yes, sorry, that's a much better one. Thank you. You are invited to look at the various apps in the course material and suggest a solution to the problem.
Okay.
So we now invite you to pay attention to what Sagi has to say.
Thanks, Doug. Okay, so. Yeah, so this is called Marine CSEM App. So you can go to if you want to run it, you can go to the index page, and then that's below the grounded source EM. So if you click the Marine CSEM layered earth, that'll open up like this. Yeah, so it's basically the same, like how to work is actually the same, so you can run it. So you can, they're importing some functions, and in the beginning, so this is the code what the Dieter, it's Mexican, developed, and we're using his code. So you can handle 1D layered earth situation and arbitrary source you can use. You can put the magnetic source, electric source. Here we're focused on the electrical source. And here's our, this is actually kind of, our focus is the kind of the hydrocarbon case in marine setup. So this is our setup. So we got a canonical model, what we call. So it's actually a 5 layered model, or a 4 layered model if you ignore the air layer. So we got a seawater, and the resistivity of seawater is rho 1, and the sea sediments rho 2, and the reservoir rho 3, and the bottom sea sediment is rho 4. So you can change those resistivity values. And also, there's sometimes in sea sediment, you can have some anisotropy. So resistivity in vertical direction and resistivity in horizontal direction can be different. Okay.
You can set the anisotropy.
Yeah. So here, what I did, you can set the anisotropy of just this layer. Usually hydrocarbon reservoir is not anisotropic. The problem actually happening here. So I just said it. You can change that, but I just said it. This layer can be anisotropic. Okay. So I think it's similar to in seismic BTI, I guess. And I think, as far as I know, rho V is usually larger than rho H.
Yeah.
Okay. Yeah. Let me know if you guys have any questions.
So that's opposite to seismic generator V.
Okay.
Horizontal is higher than the.
Oh, I see. Okay, great. Yeah, I didn't know that. I knew that there is a VT. Oh, it's a sediment. It's like a, yeah. Oh, I see. Okay. So that's a canonical model, and I put a movie, so you could, if you want to watch a movie again, you can see that. The movie was in time domain. Remember, in the movie case, we put a current and shut off, and seeing how the field's like in the off time. But the app is actually in frequency domain. The reason why we chose it, because that's the current system. So most of, I think, as far as I know, most of the commercial uranium system is frequency domain. Is that right? I'm not sure about the PGS. Not sure that's they are using either frequency or time, but the frequency domain is the main system. Yeah. So here our focus is in frequency domain. Okay. And there are 2 apps. It's similar. So the first app is focusing on looking the fields. Okay, I want to see the electrical fields or magnetic fields in the Earth. That's the first app. So before, so I think that's how it looked. But let's make it a little bit interesting. So let's set up a model now. And think about the Brazilian offshore. Okay. So what is the thickness of the sea? What is the depth of the sea?
2,000.
2,000?
Yeah.
That's it. 2,000 is not either. But that's the sea there. Okay. How big is the reservoir?
Make it easy.
Yeah, let's make it easy. Let's not do the like 10 kilometers to there.
2,000,
2,000.
below the seaboard.
From the sea bottom. So
From the seaboard, 2,000.
From the sea bottom to 2,000.
Just easy.
And the thickness of the reservoir?
100 meters.
100 meter. Okay. So what is the resistivity of the seawater?
0.3.
0.3. Okay. So I think that's so 1. How about the sea sediment?
Maybe one meter.
1?
Yeah.
Is that the case?
Yeah.
In Brazilian case,
Yeah,
1?
we have
Okay. And the reservoir?
maybe 50.
50. Okay. Well, 350. And the bottom?
What?
1 back. Okay. So that's the setup. So okay. How about the frequency? So what frequency? So transmission frequency. What frequency you want to use?
0.5.
0.5. Okay. So f 0.5. I think that's pretty similar to the setup. So here f is hertz and set with 0.5. Oh, and where do you want to put the source and receiver? Actually, receiver is fixed. So source height. That's the only thing that you can.
So 30.
Yeah.
30.
So
30 above the
10 meter?
seaboard.
30.
30.
30.
30.
30.
Okay. So 30. Okay. So we're going to put the electrical dipole source at 30 meter. That's the height. Okay. Right. So dz1 is the seawater thickness. So I'm going to set to 2 kilometers. And the source height is going to be 19. Was it 50 or 30? 70. Okay. So we're using UTM. So that down is negative. Okay. So we're consistent. Yeah, it's very important because like their conventions are very different where you go or which application. At least we're consistent. X east, Y north, and Z up. It's important. And I'm assuming the resistivity of the air as 10 to the 8. Doug used 10 to the 7, but I like the 10 to the 8. And seawater 0.3. Okay, and the sea sediment 1, and the reservoir was 50. Okay. And 1, and what was the thickness? 100. Right. So these at DZ2 is 2 kilometers, right? 2,000, and that's 1. That's the electrical field looks like. Okay. So you see here, I think it's from 0 to 10 kilometers. I think that's usually like an offset they do, or you can go even further. So you can see that the electrical dipole like kind of propagating like this, and then go down. As Doug mentioned, in the reservoir, vertical like electrical field is vertical, right? And Roberto, I think you mentioned there. I think there's actually a sign change in here.
Yeah, I was.
So we're not. I think what Jeff mentioned was actually right. So that will make a phase difference.
It's not or was. It's actually couldn't decide whether there was a no in front of you, not or what.
Right. So you can see the effect of the reservoir is coming up. And also here it's an electrical field, or as Doug showed, we can see the Poynting vector, right? Because it's kind of complicated, right? We don't know where actually the energy is moving. So by looking at the Poynting vector, so it's actually clear, right? Energy propagates up and down and goes. And here we can actually like play a bit more. Let's say, okay, what if we don't have a reservoir? Right? Marcus actually asked, oh, how about the
Let's simulate that.
yeah, how about the air wave? And then like because like energy from the reservoir actually disturbs the air waves. So let's actually go back, and I'm gonna set the reservoir back to 1 ohm meter.
I have a question.
Okay.
Here, do you have time controller in it? What time?
Well, this is frequency domain.
Oh.
So frequency we set to 0.5 hertz. Okay. So now, see, the air wave actually coming down. Right. So I think they're probably more like a air wave effect. There's no effect from the reservoir. In that way, you can actually you can ask even more specific question: what is the impact of the air wave?
What if we had more 4 kilometers area reservoir?
Okay. Yeah. So let's change the DZ2 to 4 kilometer.
4. Yeah.
Okay. Oh, so we're getting more challenging.
And the row 3.
Row 3. Right. Back to 50.
Row 2.
Row 2.
No.
Row 3.
Which one is the reservoir?
Row 3.
Row 3. Okay.
Back to 50. Okay. Yeah. So that's how it looks like. But by looking at this diagram, take that so you can understand what's going on. Oh, that's how the field looks like. Energy propagates down, goes up. There's an air wave, but it's still hard to see. Okay, how much difference that I can see, right? How my data looks like. Right? So our receiver is usually on the C bottom, right? As I've showed. So let's go to the other app. Oh, I think one thing here, I'm going to go back to electrical field. Now, let's think about, let's consider the anisotropy of this part. Right? I'm going to set the anisotropy to, like for instance, 10. May not be the case. Let's go back to 2000. And back to 1. So well, let's not go there. Sorry, I was trying to show if I change like increase this value and the electrical field goes more vertically. I think that was my imagination, but I think not 100% sure at the moment. So I'm not going to go there. So okay, so 100 meter. So that was the case. Okay. Now I'm going to go back. I'm going to go to the data app. Yeah, here we're focusing on the data. So what does it show is it's not, these two apps are not connected. You need to set the model again here, although parameters are same. And I set that as you can set the 2 different sets. Okay, so I'm going to compute the 2 different data sets based on these parameters. So one, like this one could be 1, and this could be other. So I call this as a response, and that's the background. Okay, because here I want to compute one model, and I want to compute the other model and compare how much difference that I have, for instance. Okay. So I think this was the canonical case that we said before that Doug showed. I think it's with the optimistic case, got 200 meter thickness, 1,000 meter below. I got a response, red one, and then that's the background.
I'm sorry, which model is this? Is the last we
left one is the red, the right one background is the black.
But
No,
it's another model.
Yeah, so we're going to set our model, this one. Okay. So here I'm just explaining what the functionalities are. So you can change to magnetic fields. There's no HX component, so it doesn't show anything. So you can see HY, you can see that. So there are multiple components. And also you can see impedance. Sorry, I think there's a bug. For real component, imaginary component, amplitude, phase. Okay. So you can plot in a log scale or linear scale. Okay. And you can fix the value. So if you want to fix the, let's go back, and minus 200 to 0. And you can fix your values. So in that way, you can kind of focus on certain things. Okay, so let's go back and set what we set. So what was it? 1970. And Rx height is 2000, I guess. And okay. What is DZ1? 2000? Is that right? 2000. DZ2? DZ2, what? 2000. And DZ3? 100? Okay, so I'm going to set the same. 1000, 2000, 100. And the resistivity of the reservoir was 50, right? So now we set. And I'm going to start from the amplitude and log scale. Okay, that's how it is. But what is the noise level, Sergio, for usual marine EM case?
10 to the minus 15.
So 10 to the minus 15 is about here, right? So although we got really big signal here, it's hard to see it, right, with that noise level. So what some other companies they're pushing really hard, because this is a relative electrical field. If you're putting more current, that noise level can go down.
Yes.
But now you can.
This strength of this electric field is similar to the commercial ones, the service companies that you are using.
Oh, this is we're normalizing, so we're assuming a unit current. So we're dividing all the response by input current. So it's normalized. But so if you're increasing the current, then that noise level can go down. But then that's the reason why they're building putting more current and making a larger dipole. Okay. And also remember the inline and broadside. So inline is kind of like a design for 2D survey, right? So you got a source here, and the receiver is like here, or in 3D. So that's inline, okay? But you could do on both sides. That's the cross line. And so I think to get the both side, you need to do a 3D survey, for instance, right? You need to put a receiver here and also here. Okay. So, and then they may have a different kind of signal from the target. Okay. So let's take a look. So now here the plane X, Z, and Y, Z. That's actually like we're changing the plane. This is X, Z. I'm changing the plane to this plane. So what is the main component you may measure here? Here we're measuring the X component, which is inline. On that plane, what is the main component?
Y.
Y? Electrical. So at that point, what is the main component of electrical field?
To the electrical.
Oh, this is the X direction. And that's X as well.
the EX.
Yeah, yeah. Well, still, like it's right. Okay. So X component is the main component. So let's see the X component of electrical field at the YZ plane. That's quite different. Right? So you're seeing the difference is much smaller compared to the inline. Right? So that's the reason why like their main component is inline electrical field. Okay, and let's go back to XZ, and you can look at the phase. Right? So this is a frequency domain response. You got amplitude and phase. And we have a case history that shows amplitude and phase, so we can take a look how they are different. Okay. Let's go back. What else? And so, have you guys heard about non-uniqueness? Okay, so that's good. So let's say there could be for a given data set, like where data set is just decaying in this case, right? There could be a whole bunch of different models that can actually explain this data set. And one of the well-known non-uniqueness in marine EM case or DC case, DC resistivity, it's a resistivity thickness product. So let's say you got a resistive layer, and then let's say rho is 1, then thickness is 10, and your resistivity thickness product is 10. But if you have thickness 1 and resistivity 10, you got the same resistivity thickness product, for instance. Then your response is exact, but not like very similar, I guess. So that's well known, non-uniqueness. So let's actually test it here for the marine EM case. So that was for DC, but that doesn't necessarily exactly in the marine EM case because we've got both DC and EM response here, right? So we have charge buildup and EM induction. Both things are happening here. But let's just try and see if we can, how the response looks like. So I'm going to set the reservoir thickness product the same. Okay. So for our case, rho was 100, right? And so resistivity thickness product is 10,000. Okay, so for this case, this was 100 and 100. So what are the other cases? Just pick a value.
First, we set 50 hertz.
50?
The hertz 60, yeah.
Rho 50?
Yeah.
Okay. And the thickness? 2. So actually, let's do that and see how the response looks like. 50? What's your guess? Exact? Different? Or very different? What's the guess?
Very, very similar.
Okay, very, very similar. Oh, give me a sec. Supposed to be. Am I missing something?
Yeah, the whole tree in the first.
Not 50. The whole tree for the first model.
The first model.
Oh, right. 100. So, yeah. So I think that like a non-uniqueness still holds for at least for inline component. And how about the broadside? So we got the inline. Also, we can have a broadside. Pretty similar. But there's probably still a little bit of difference here compared to the other case. So I think it's the same. Now, so I think, but if you have some noise here, then you may not see any difference. So I think that recognizing that is very important. So let's say if you knowing both resistivity and the thickness with this CSEM will be pretty tough. Right? So probably you need some seismic image, then you can get the true, well, not true, but like pretty good thickness and resistivity together.
Most likely one.
So you can help each other, yes.
Because sometimes we have two anomalies in different levels.
Right.
And to try to constrain the result we have.
Yeah, so that's the reason why people want to constrain or put more a priori information to their interpretation or inversion. I think that was it, I guess. So yeah, so it's there. So yeah, hopefully you guys can enjoy it. Any questions?
Can we set an isotropy in the second
Right, I see. Okay, so what's the ratio, Sergio? 5. Whoa. But okay, is that the usual?
No.
No. Okay, so let's start from 5. Oh. I think I'm gonna set this back to 100 and 100. Yeah.
We might need to
That's weird. Okay. Okay. Wow, that's huge. Yeah, so that's the difference. So I think that's the same case without the anisotropy, and that's with anisotropy. It increased a lot, right? So we're increasing that. So the resistivity here is based upon horizontal resistivity. So but the 5 is too big, I guess. Like, what's the an actual practical number, Sergio?
Maybe 1.5.
Okay, 1.5. So I think it's not. That's right. That depends. Yeah, 2.
It's vertical over or horizontal.
It's like, so 2 is like a rho v is bigger. Yeah, rho v over rho h. Yeah. So I think any other question here?
So the method is more sensitive to the vertical resistivity than the horizontal, because when you increase the vertical resistivity, the response of this model is higher than the model, than the original model. You see it?
So we're increasing. So
when you increase the
yeah, it is sensitive to vertical resistivity, to this inline setup. Okay. No, any other question here? Yeah. So that's one app. And well, what about using the inductive source that was shown, right? So ground source, great, but you can still use the inductive source as well. So I'm going to use the same app that I have shown. Here, so TDM horizontal loop layer. And what the Japanese are interested is actually SIFO massive sulfide. It's a big conductor, right? So remember, inductive source is, it's good to find the conductor. And now situation is a bit different. We're in the sea. So you got a loop here, right? And then you're going to have some conductor, so massive sulfide. And let's say they are interested about 20 to 50 meter depths. And that's sort of the setup. Okay. So now, before we put the source in the air, now we're actually putting it in the sea. Okay. So what's going to happen? How the electrical field or how the currents looks like, or electrical fields looks like. where the wave propagates. So that makes a complication now, right? So what is the conductivity of seawater? Conductivity of the seawater. Yeah. So we're going to set the, what is the opposite? Or 3. And the sea sediment was 1, right? So I'm going to set the first layer to, I'm going to set the first layer to 1. And the massive sulfide, it could be pretty conductive. I'm going to set to 10 centimeters per meter, which is pretty conductive. And back to 1. And I want to put that into 20 meter below and the 20 meter thickness. The model looks like this. So now this is the sea, right? And that's the sea sediment, and that's the massive sulfide. So I changed it a little bit from you guys' suggestions. So now you can set the V mean and V max. And also, I changed it so now if you click it, that's updating. And if you're not clicking, so if you're clicked, then it's every time it actually runs the formalling. If you, in this case, it's not. So now I want to run. And I want to see, let's say, electrical fields. Oh, right. And that's 20 meter above from the safe pole. And let's look at the electrical field. Doesn't move at all that much. It's very different from what we've seen before. And why is that? Where is the source?
Inside the conduit.
Right. So it diffuses very slowly, right? If you're in a very conductive movement. Oops. 15, 20, 25, 30, 35. Wow. So let's go fast. 50. Now actually it hits the target. Right. So I think the image is quite different, right? Like we got more diffusion in the conductive layer, right? Because it's a conductor. 5. So I think there you're actually hitting this massive sulfide target. 60. I think you need to go fairly late, so a couple, like a millisecond level to measure those. That's 70. How the data looks like. Oh. So yeah, I think you could try for a given setup, you can actually change all different parameters and can actually think about marine case for this as well, but for a shallower target. Okay, I think that's it.
Okay. Great. Okay, well, I'll take a quick break, get a coffee.
Okay.
Yes, I just updated. So, like if you're trying to run now, it probably take a little bit of time, I guess, too. Yeah. Oh, that's true. Sorry.
I like to keep
Yeah,
up.
we're alive, so
Very dynamic group
we're
here.
updating. Yeah, a lot.
Sorry, I didn't get that. Again, no worries, no worries. A long time since I've seen.
Oh, I see. That's a pro, yeah.
Remember that from like elementary school?
Like they usually have a cover, yeah. I have a pencil.
Oh yeah.
Oh my desk. I love it. For an answer, I think if you clone again.
Oh, you want me to clone again?
Yeah,
Because
like-
I do it on Monday.
Right, so I think there are quite a few things change it, so you need to clone again.
Okay.
And I think in theory.
Okay.
Are you causing problems, Jaja?
I have a lot of problems. Sorry.
So this, I don't know if there is a mini and max, what are they?
I think your kernel died. Fresh. So your kernel died, I think, because you can go back.
So do you remember you have a mini max?
Yeah, so that's that's setting the mean and maximum value.
Of the scale?
Yeah, just for the column, just for the visualization.
Oh, okay.
Because like sometimes that helps.
Okay, and also, can you use that the CSEM system or have to model some kind of like GPR system, like transmitter system on the ground?
Yeah, you could try, but I think that is set. Can you run it? Could, but the setup is fit for. I can still try to use it. Probably.
Because I don't see there is any app for GPR systems, so I was wondering if
You can definitely try.
I actually tried to use their
1.6.
So I want to see, use the second app where you have your background and so on to see the data.
This is good. This is going to be hard because it's 10 kilometers. I said that yes, because this is not really set up for GPR. So you're not going to see the 10 kilometer with GPR.
But you can still play. Let's say you can, let's say just for example, the frequency.
1,000 is fine. Like 1,000 is fine.
So they're high. So that's the source of their.
Yeah, you can definitely play with it. So you can hear it. Source height. So that's the. So I think it's probably better to see here. So you could change for
What
your
is HED?
horizontal electrical dipole.
Oh, horizontal.
Yeah, so it's a dipole in X direction. So actually, that's quite similar to GPR. Because like GPR is an antenna. Like
Yes.
So. I think this code is set up that could work for GPR. I think, as far as I know, you can. Let's say if you put the stuff on the surface.
Yeah. So the source is transmitter.
Yeah, sources are transmitters.
So you have air. So basically they're the same. Because you don't have the, you adjusted the okay, you already have that.
Yeah, I think now we need to. Yeah, so I think you could use it.
So you cannot see the difference, right?
Oh, yeah, no, I think no, at all. You're not going to see that. Yeah, so definitely, let's go back to the same case. Here. Now, let's just increase the frequency. Here. Reference is 0.5, where you can see a lot. So actually, let's make it basically the same. Okay, does that make sense?
Yeah. So now you change the frequency.
Right, now let's change the frequency to even 100 hertz. So I think those are numerical errors. Well, it's very small. I think the response decaying a lot, right?
Because of the high frequency.
Yeah. So I think this is what
But this is this is how many
yeah, but your noise level is here.
So you don't plot anything that's your zero. Okay.
So I think the minimum spacing is about 100 hertz. So I think it's decaying much faster. So put down. That's a bit extreme because this is the C, right? So you're putting the really conductive. So let's say 1 or 10.
So I think with row one. Row one basically is air in this case, right?
Right.
So you can put very high, right?
Yeah. Well,
Maybe same as air.
Yeah. So that's the. I'm thinking about the air. So.
But here.
Oh, I see. So you could actually move your source to 0. Source and receiver is on the surface.
Right.
So now. Yeah, so you can definitely use that to test how that's. And I think here, let's say 1,000. Okay. And if you go higher frequency, there's a big attenuation, right? Attenuation is getting bigger and bigger, right? And there's skin depths.
So which part is the attenuation?
So this is 1,000. Okay. Let's make this one. So this is black, red. 100. See that? Now you start to see something. So as you go higher frequency, it's
So in this case, if you set the pole, you don't see the limit, right? Let's say we have 100 resistive.
so you kind of see that.
Yeah,
There's some difference. And then if your noise level is higher than this, then you can do that.
So this is a frequency.
Yeah, it's frequency. So, oh, I think it's very, like, it's hard, but maybe you should have But that Meridian case, it's a very ideal case because you're in the Meridian setup. You have very noise, like a small, like a very small noise.
So the noise is your, let's say, like, so we're looking at the electrical field. So let's say, how do you determine, like, let's say if you go to a field, how do you say, like, operational noise?
Well, like in practice, like your noise is practice. Like depends. So you just plot the data, and if the data goes like that, then okay, I think I got 60% here, and also there's as a receiver itself, it has a certain minimum like a value that it can measure. So that's one thing. But for the field case, like you actually measure how.
So in my case, so as I mentioned, so they measure, so the system they measure is like 3 meters apart. So they're trying to measure and this is just the right about
Aí no
and
Friday,
then
você vai
the kind of send the pulses, so this is your pulse. So then this is TX and then it's RX. So the RX will vary. So it's like, so if you plot it, the measurement is like this. So it tries to attenuate and then to certain point, so the amplitude is like constant.
Yeah, I'm not sure. I think
So then,
E fecha e fica direito.
so we turn off the transmitter and then they only kind of run the system. So they will measure something like that. So they will get something like this. But the problem is.
So it's like a seismic data.
So to me, this is totally like normal too. So after this point, but the problem is, so we do some kind of data processing, and in this part, this is about some big surface. They kind of do some data processing, and then, so what they did is, so they send several pulses, like they send, let's say,
What's the frequency?
so they have a wide frequency. It's not that you here's their input signal.
So it's a nanosecond, right? So they're putting like a very like a fast pulse.
Yes. So that's in the frequency domain, that's the input signal.
Yeah, so I think it's 0 to 100 megahertz. I think that's mostly 60 megahertz. 60 to 70 megahertz is the maximum. That's the frequency.
So we have the sentence pulse. So they kind of have each pulse. They have a really output space. So they get 1, 2, 3, 4. So they try to.
What is it called? Like 1, 2, 3? Is it
different frequency? No, it's just so they kind of. I think they send the pulse and then they measure. So the checks in the pulse, the RS, the RX, the with receiver married, they get
So,
so now they send a second pulse and then they matter third pulse.
Oh, so they
Repeat.
Oh, I
Yeah,
see.
they repeat.
Thousand times.
So 1,000 times. So then, what I noticed is interesting is that one follows different pulses. So they actually they kind of stack up changes the simple ratio. So they stack 1 to 100. So basically they kind of average 1 to 100. So they get
Whoa, wow. I think this is probably fine.
Then you do another from like 1 to 200, they get another one. There is still the baseline, so like, because they have the noise, so they kind of cancel each other. So you will see a kind of smooth line after they stack.
Okay.
But there is a kind of shocks, right? Between those. Do you have any idea why how that? So like the baseline, like for example, so if you use that 1 to 100, you can kind of average value here is like 128. So the next area you get is like 129, and the next again is like 130.
Actually, just looking for a model, I think I can imagine why, that's my expectation, like, people get much different, like. So, like, it's not like, if you're.
But their total model, like for example, is this it's like you won't see it different.
Okay, so we're all going to go to Salvador next. That looks like a cool place to get some.
Salvador.
Yeah,
That's the problem.
learn to do a few dances, martial art dances, eat good food. Yeah, why are we in Houston? I mean, it's all Petrobras. You could have just invited us to
Salvador.
Next year.
What I'd like to do, we've got 2 case histories. I think we'll probably use that just to kind of round out the afternoon. The first case history is actually with respect to de-risking using CSEM. And the second case history is concerning work in the Saudi Arabia area and looking at marine. Oh, no, wait a minute. That's later.
Yeah, that's smart.
This one's in the North Sea.
Yeah, this North Sea.
And then there's only one, I think.
There's
There one?
2.
There's 2?
Second. Oh, it's the methane hydrates. That's good. Okay. Good.
All right.
So this comes from Lucy McGregor from Rock Solid Images. So you know her.
That's great.
Cute. That's that. So the area is up here in the North Sea. It's the Hoop Fault Complex. It's in a place called the Barents Sea. And the idea is that, the seismic can, determine whether there's, where the reservoirs might be, but it's difficult to make that discrimination of whether it's, really an oil and gas reservoir or whether it's low hydrocarbon saturation. Maybe it's just gas fizz, or maybe it's just a brine. So the idea is that you want to combine, seismic with some borehole stuff with CSEM, and find some more about what's going on, get an idea about what the fluid is, the porosity, clay content, and importantly, the hydrocarbon saturation. So that's the task here. And what we're going to see is that the marine CSEM is a component of that, and going to get the electrical resistivity, We're going to be looking for resistive features that are coming out, and then that gets combined within a rock physics modeling to give you some estimate of what the saturation of hydrocarbons is, and then make a decision about whether to drill this or not. So it's a de-risking. So why does it work, or what's the underlying thought process here? So this plot here is acoustic impedance. It's from one particular drill up there. It's the acoustic impedance, and we've got resistivity on this axis. The various color scales here. So the blue is just indicating rock that's wet. The red is something that's 80% gas. The yellow is 80% or 20% gas, so it's just like gas fizz. The green is 80% oil, and black is just in situ. So those are the different rock units. And the question is, okay, what is diagnostic? And if you look up here on this axis here, it's the acoustic impedance. And, you know, blue, yellow, green, red, black, they all have the same kind of acoustic impedance. So if you had an acoustic impedance at this value here, we don't actually have a scale on. But if you had acoustic impedance, let's suppose it was right at that value, you know, it could be any of these 4 units. So it's just not, it's not diagnostic. Whereas if you look at the electrical resistivity, you see that the two things that we're interested in, 80% oil or 80% gas, so the two hydrocarbons, that they're over here on the right-hand side, you know, sort of at 30 to 50 ohm meters. And that distinguishes it from something that's just wet or something that's sort of 20% fizz gas. Right? So that's a real separation on the resistivity. If you go to a different area, you have essentially the same thing. So there's, on this axis, on the resistivity axis, there's a clustering of non-hydrocarbon versus hydrocarbon rich, and there is no clustering if you go up on the vertical axis on the acoustic. If you look at the resistivity as a function of hydrocarbon saturation, this is what the curve is. So if it's low hydrocarbon saturation, the resistivity is low, less than maybe 10 ohm meters. And then once you get to about 70 or 0.7, 70% saturation, the electrical resistivity is more like 20 ohm meters. And then increased saturations beyond that, it basically just skyrockets to give you, 100 ohm meters or more. So this curve here shows how and why you could differentiate hydrocarbon rich versus non-hydrocarbon based upon the electrical resistivity. So here's the survey. It's done in this particular field. So they've got a ship. Actually, it's they're towing both the seismic and the CSEM in the same boat. There's 6 lines of seismic data that are obtained, as well as co-located with the CSEM. So here's the CSEM transmitter, and here's the receiver coming up here. And so you've got this line of receivers. The nearest offset is about 30 meters, and then the largest is just about 8 kilometers. That's a seriously long cable to tow. And the frequencies that they're using are 0.2 to 3 hertz. There was a number of lines that are done this way, and then there's a cross line that goes through here. We're going to be looking at this cross line. There's actually 4 wells that are of interest. There's 2 wells. There's alternative, which is up here, and central, which is here. Those are the control wells. So we're going to say like, okay, we know those 2. Alternative is dry, and central is a producer. In here. So we've got 2 wells that are going to be controlled. One's dry, one's and then there's 2 wells that we're going to use as validation wells. There's Hansen, which is up over here, and Ballen, which is over here. And we're going to use those as validation wells. So we're going to do the CSEM along this line and make some estimate about what whether we should drill or not based upon the resistivity.
Is that induction source?
Yes. Yeah, so it is a harmonic source, but it's low frequency. And it doesn't cover a huge range, but there's a decade there, so that's significant. So remember the scaling depth depends upon the square root of the frequency. So between the low frequency and the high frequency, if there's a factor of 10, that means there's a factor of 3 in the depth of penetration of those 2. So that's enough to get some vertical discrimination. So the CSEM is done along this line, and here's the data. So let me try to explain what this. First of all, here the data are going to be represented as an amplitude and a phase. So sometimes we talk about real and imaginary, it's fine, but you can also do amplitude and phase. There's a lot of lines across here. So each line is what you have with a particular receiver. So remember, there's 31 receivers that are going out nearly 8 kilometers. And the first receiver is only 31 meters away from the transmitter. And as the ship is moving along, these are the data that are obtained in that first receiver. They're the highest values because we're the closest to the transmitter, only 31 meters. And we're just sort of moving along. The progressive lines in here are due to the fact that you're going to receivers that are farther away. And so the amplitude, high amplitude is red, low amplitude is blue. So as you go down this way, you're going down farther and farther receivers. And as you're going along this line, you're just like, okay, that's what I'm measuring as I'm going. Now, if you look at the amplitude, there's nothing really obvious that jumps out and says, wow, there's a big anomaly. Maybe it's a little bit darker, but there's nothing really obvious. So the information is actually in the phase. So this is the same thing, but this is the phase, and you can see here that there's something really interesting happening. So there's a significant response over the central reservoir, or the central region, which is up. If we look at the seismic data, so color-coded with respect to amplitude, we'll end up with an image that looks like this. So there's a lot of faults that are in here, and these lithologic boundaries, refer to 3 units that they've got. I can't really even pronounce them, but there's three different units in there. And what we're really interested in is what's going on kind of in between the top and the bottom of those 2 layers. So they have some wells, and from all the seismic work that's done, I don't exactly know how they got all of this information, but here's 3 images. There's the lithofluid bases, there's clay content, and there's total porosity. From our perspective, what we're interested in is the 2 control wells. There's alternate in here, and there's central in here. So those are the two wells. This one was productive, and this one was not productive. So let's go back and revisit the physical properties. This is kind of a repeat of what I'd shown you initially. So on this axis here, we've got the P wave velocity, and here we've got hydrocarbon saturation. If you look at the P wave velocity as a function of saturation, it changes greatly between no saturation and maybe 20%, and then beyond that, that doesn't change. On the other hand, the electrical resistivity starts off really low if there's no hydrocarbon saturation, increases, and then at about this 60, 70%, really starts to increase markedly. So this is a log scale here. So that means that the resistivities are really good. So I would take the CSEM data, so it's now multi-frequencies, it's spanning that order of magnitude, and we take those, and those are inverted using a 2D, on a 2D section, and the inversion results give something like this at central, okay? There's a very, excuse me, high resistivity. So in this case, the red is resistive. The red is like 90 ohm meters, and the blue is 10. So there's a couple of parts that are resistive, this region in here, and then the next most resistive part is in this region in here, Hansen, which is a validation well, and this was the other validation well. So you can see that it's much more conductive here than here. It shows up a little bit better on my own personal screen than it does up on here. But so the central, which is the most productive, is also the most resistive. And from a point of view of the validation wells, the Hansen seems like it's more resistive than the Vala. So those data are taken in, rock solid images, then incorporate that with all of this other information and all the information they have about the rock physics, and they basically kind of combine that to get a final hydrocarbon saturation. So all the stuff that goes in here, we have no idea really how they do that. It's their rock physics model and everything that they know, but they've come out with this as being a final saturation model. And this region in here, okay, where you have central, is the highest hydrocarbon saturation. The next most highest carbon saturation is this one here, Hansen, which is the one of the validation wells, and Vala over here is. So of those two, then this is the higher priority to drill there. So anyway, that's the case history from that. I think that's probably pretty typical of what people are doing these days. Just taking data, inverting it. Maybe they're doing it in 2D. Maybe they're doing it in 3D. I don't really know. Certainly at the time this was done, 2D inversion was about what they're doing. The big thing with respect to this is including the anisotropy of the conductivity to get the right sort of depths, and then just do this.
What about the vertical resolution? Because maybe, for instance, we have one reservoir 1500 deeper, and what's the minimum thickness for you that you can distinguish between one reservoir of hydrocarbon? 30 meters, 20 meters, 10 meters.
all of those things are going to depend upon, you know,
several.
yeah, just so many different factors, and for that you really need to just do a modeling, set things up.
What's the biggest issue for the vertical resolution?
Vertical resolution. So now you're talking change in skin depth, so that you know the frequency band that you're looking at is important. Frequency band and other, I mean, a priori information is we'll see tomorrow in inversion. I mean, you need to be able to constrain things. I believe in this, you know, in getting this image out here. I'm pretty sure they were using information from seismic with respect to, you know, bounding the, you know, the tops and the bottoms of these layers and putting in other pieces of information. If you just look at the electromagnetic data themselves, there is not really good vertical resolution, especially as you get down to depth. So everything kind of depends upon like the skin depth and sort of one of the rules of thumb is that, you know, your resolution is only going to be like a fraction of your skin depth, right? You know, you can't really see deeper than a skin depth or.
But there's a magical number like seismic you have lambda over 4.
Yeah, can't do quite that. That here. Yeah, I think the best that I might be able to offer in that regard is that if you are doing, let's suppose you're in one dimension, right, and you're doing a sounding, and then you're starting to see, well, how many frequencies should I measure in order to really get an adequate electromagnetic representation of what's there. If by the time you've done 4 or 5 frequencies per decade, you've probably extracted most of the information. Yeah, so you can kind of work back from that and see, you know, you've got a fraction of you know, of the skin depth as far as resolution. That's kind of, so that's not great, but still it's you know, there is some vertical resolution. By the time you put in additional information and constraints with respect to, you know, seismic boundaries, yeah, you can start to you know, to pick things out, and then you've got the lateral variations that. But you know, at some level, you just have to appeal to the modeling, and as I said right on the first day, and maybe worthwhile emphasizing again, there's 2 aspects of this. One is to redo the forward modeling kind of with and without, see if there's much difference. But the other is actually to carry that through the whole process and put in all of the other information that you've got and use your inversion algorithm and then see how much difference that makes. And that's really final proof.
I'm speaking about that because in Brazil we have one case. There's a amplitude anomaly, AVO with gas, and they are trying to extend the discovery. But the extension doesn't have anomaly, and they are trying to use the resistivity. But for the seismic resolution doesn't indicate that region there that the resistivity word indicates.
I'm sorry, the last sentence again?
For the extension part of the structure, the seismic anomaly doesn't show nothing, but the group from resistivity were indicating to drill there.
Okay.
But we didn't drill.
Oh.
It was just one case on study, but we didn't drill.
Well, we don't know then, do we? That's exciting, yeah.
That's my question, because the seismic resolution, we cannot solve the problem. So that's my question about the resolution of the
But is there a possibility that whatever hydrocarbons you've got out
Yes.
there could exist, but not really give you a strong seismic signature, but might still be enough to see from an electromagnetic viewpoint? I don't know, that's really a question.
Yeah, probably that part maybe 10 or 5 meters of reservoir with hydrocarbon, but the seismic didn't show nothing. Yes.
So I think in basically the exploration, normally, yeah, one challenge you are facing using seismic is because the wavelength of seismic wave is very long. So normally, let's say if you want to locate a boundary between two zones, so you can do seismic, and then but seismic cannot see, like, let's say if your boundary is at 100 meters from the ground. So you may only kind of estimate maybe the boundaries between like 200 to like 50 meters. So that's the range you may get from seismic inversion. I think the question he's asking is, can you use EM like kind of techniques to kind of get a finer resolution, just kind of limit the range of the uncertainty of where your boundary located?
Right, so in general, electromagnetics has got much poorer resolution than seismic, certainly for the cases that we're dealing with, right? But if let's suppose you had a really thin layer and it turned out to be like really conductive, okay, then you might actually be able to see it quite neatly. So if you imagine, something that didn't have a particular seismic response, but was really electrically conductive, then you might see it. Otherwise, the only way, you have to come back to skin depth. And if you, in order to get a small skin depth, you need to have high frequency. So this is why in the geotechnical, if you ever watch your geotechnical engineers pull small devices over freeways or something, and they're either looking for pipes or sometimes they're actually looking for just wires. So now we're talking resolution of centimeters here, right? You can get that with electromagnetics. You can get resolution of centimeters, but you need to have a very high frequency. So that's where you get GPR types of signals, and now you can see stuff in centimeter scale. But that centimeter scale has to be close to your instrument, because if you put that centimeter scale down at the end of the room, that's too many skin depths away, and you don't have any signal. So that's where it kind of comes back that your resolving power of your EM experiment is really kind of related to the skin depth, and sort of like a fraction of that, and that's about as good as you can.
Can I vary the frequency of the EM source?
Mm-hmm. Right, but the point is, if I have an EM survey that's got a skin depth that goes all the way to the back wall, okay, and then I'm going to change this, I'm going to increase the frequency, so now the skin depth is a little bit less, a little bit less, less.
Want to reach the...
Yeah. Now it's not going to reach there. So the things that reach there are really broad wavelengths. So they don't have that much resolution. And if I bring things back, then I just don't see as far. So the result is that by the time I get to the end of the room, there's really only 3 or 4 frequencies that are very sensitive to that. They need to have low enough to get there, and you need to have enough of them to.
So the resistivity, how the thickness affect the skin depth? The thickness will affect the resistivity. If I have one material with maybe 15 meters
Mm-hmm.
and 10 meters, the total resistivity is going to be different.
Right. So here's where Sagi was talking about the equivalence with the resistivity thickness product in the marine EM. So for some surveys, like the DC resistivity type of survey, it's more of a resistivity thickness product. For EM waves that are going down, it's often that's more of a conductivity thickness product, and that's where I talked about the conductance. So if you could have two models with the same conductivity thickness product, okay, and they give essentially the same results. It's an equivalence, a trade-off. It's not. And in order to resolve that, well, you can't do it just from the data, but if you had some extra information, say, okay, I know what the top boundary is or something like that, then that actually might be enough to add something, and then now I can go ahead and help these things.
Moving up to the source side, Liam Downson, I know if you.
Yeah, I know that. Yeah.
He gave us a course here, a one-week course, and he claimed that as the EM signal we register is very weak, just like seismic, even weaker than seismic. He claimed that it would be better if the seismic, if the EM source was off when the register happened. So he claims that we should use a impulsive source, just like seismic, instead of a continuous source. Would that help the resolution thing, the resolution issue? What do you think about that?
It can because the thing about an impulsive source, you don't have this primary field that is continuing on. So now it's a matter of, okay, I'm going to switch this off, or I'm going to have a waveform that's actually got enough energy to go in, and then you're measuring stuff in that off time. And if you look at airborne surveys, that are used in mineral exploration, the equipment that has been developed and the sensitivities, the time domain systems often outperform the frequency domain systems. As we saw though in that first example today, I mean, in principle, there's not so much difference. Everything always comes down to signal to noise, right? So depending upon the noise that is going on for whatever you're measuring, whether it's a time domain or frequency domain, you can kind of tilt the balance like, okay, this is a little bit better than that. So signals are small, but if noise is even smaller, then you're good to go.
So you mentioned about the signal to noise ratio, but you also said basically if it goes beyond the skin depths, you cannot see anything. So for those so the skin depth is a given, for a given system and frequency. So how far you can see, it's also dependent on your signal to noise ratio.
Right. So the idea that you only see down a skin depth or more, I mean that's just a general kind of rule of thumb, right? But after that, then it's like if I had really, really accurate data, I might be able to push this so I can see 2 skin depths.
So it won't be like order of magnitude. And even you have very very small noise, you won't see let's say 10 times of skin depths.
That would be pushing it. That definitely pushing it. The whole skin depth is to kind of put things, give you some kind of a number that you got a first order approximation about what you could see. So the concepts that, okay, with an EM system, the farthest I'm going to see is like a skin depth or maybe 2, or a diffusion distance, you take the latest time, or maybe 2, right? That kind of puts things in perspective. That's already a very, very important number. And then the fact that if you're talking about resolution, well, you're at those deep depths, you're only going to get a fraction of what that skin depth is, or what that dispersion distance is. And you saw that from the plots, right? We showed you what the currents are like. I mean, there's no way you can combine those and get 20 centimeter accuracy at a kilometer depth, which is kind of the problem that you're thinking about. Actually, with respect to that, if you might, on Friday, what we'd like to do is to devote a little bit of time so that people here could talk about some of the problems that they're dealing with. And there's one that came up over lunch about the potential for using electromagnetics and potentially even maybe induced polarization for pyrite halos for hydrocarbons. Right? So that's an area that you're interested. We're very interested in what you have to say with respect to the AdRock thing and just what they're claiming. And we could just kind of take a look at those problems and say, does that make sense, or does it seem reasonable, or what kind of questions should be asked? So not that we're going to answer all the questions, but at least it would be something that we could bring up and discuss and use the information that we've done so far in the course to address two problems that are of interest to them. And maybe others too. I mean, does anybody else have? Are you involved with with a problem in which at this point either EM has been applied in some case, or now that you kind of see the gamut of things, like might be a question like could electromagnetics help in this regard? It'd be interesting just to throw that open and just kind of discuss it a bit, right? So.
About the advanced model.
I will talk to him about this model of natural prioritized region using time domain EM. Because the guys of that area want to know where the oil is in the old fields that they have, and they notice that the oil that is remain there is associated with a gas exudation, and this gas exudation provoke a formation of pyrite over this area, and it's proposed to use the time domain to map these pyrite zones, but we don't acquire this data.
Well, another thing would have potentially some bearing on that is the material that sort of Lindsay has been working with, and other people are now too, and that is using these casings as extended electrodes, because now you can ignite stuff at depth. And that was one of the motivations for people in North America to look at these, because it's exactly that same situation. You've got an oil field, and it's first order, it's been kind of pumped up, but then you don't know, okay, what's left, right? And so you could come back and try to redo your seismic, but if it would be possible to actually do an electromagnetic experiment, okay, in which you could drive energy into some region at depth and measure something at the surface, I mean, you actually might be able to see if there's something there yet. And that's where the extended wells as extended electrodes can come in, because just funnel energy right in.
DC acquisition.
Yeah. Well, it could be, but it could also, they're also looking at it for time domain. Yes. Chevron is probably one of the most active leaders in that. So in that sense, now here's your surface. Maybe you got a well that's coming down like this. You got another well that's out here, and you take a generator and have a current, either time domain or frequency domain, and you hook one up here, and then maybe you measure, electric potential someplace here, or maybe you actually even attach it to here. I mean, all kinds of configurations are possible, but the idea is that if I hook this up as an extended electrode, now I'm funneling current. So if I got something out here, okay, then there's current that's kind of going to be going out here and directly igniting or exciting that particular body. So now I'm going to get charges that are going to be in there, and I might be able to pick them up using a potential meter. So that's an area that's very much activated, and you could do that at a DC, but you could also do it with a time domain experiment and then see how the signals change as a function of time. So I think that's sort of the state of the research art at this point. And it's a tough problem, it's a challenging problem because you've got to deal with these well casings and you've got small signals. But again, measuring equipment continues to improve, and undoubtedly there will be some advances that are made. So let us plan on Friday. So Sergio, you talk. Denton, you talk. Okay. And anybody else? You can think about it. But if there's just this is an opportunity just to throw stuff out, right? Like, oh, okay, well, what about this? And or even a question of like, okay, I've got this. We're actually having some challenges with the seismic. Is there any way, any particular kind of survey, in any geometry that could actually maybe help me someplace? Yeah. Okay, then there's one last thing I want to do today, and that's a case history that has to do with methane hydrates. So if you look at the map of the world, this is concentrations of methane hydrates. They're primarily on sort of subduction zones, but they occur on many of the coastal areas from the point of view of offshore, Brazil and down south, Argentina. We've got some. Those are green, so that's 5 to 50 kilograms of carbon per square meter. Maybe that's a resource. We were talking earlier or a hazard.
Yeah, that's what I talk about, that the South Brazil is Pelota Basin. That's the red and blue one.
This one here.
Yeah.
At North Brazil, we have as well in the Amazonas mouth, Amazonas River mouth.
Right up in here?
No, a little bit in the north.
Near the equator line.
Follow the coastline.
Yeah.
Going.
Near the equator line. Yes, that's
Yeah.
yes.
Oh, okay.
But it's,
So this area, wait a minute, where's the bottom boundary of Brazil?
that really-
Yes,
yes,
right in there?
around it, yes.
Yeah, so this is a very high area. That's 100 to 1,000 kilograms per square meter. Hotspot. Japan, okay, it's got sort of a lot off of the coast there. They are actually going to be mining. I believe that's this summer that they're planning to start a test producer. We'll definitely hear more about mining gas hydrates as time goes on. This is a case history. It was put together by Karen Weitemeyer. She was a graduate student at Scripps, and it's an area off the west coast of North America in Oregon called the Hydrate Ridge. This is an image of it. We're going to kind of step our way through. So here's the here's the basic setup. There's an accretionary complex zone off the Cascadia subduction zone. So we have on the west coast some areas where it's actually subducting. There's also transform faults that go. There's the San Andreas fault. The seismic comes along and they see a great big reflection at depth. And this is a sort of what they call the BSR, the bottom simulator reflector. And it's an acoustic impedance contrast that exists between the solid hydrate and gas. So that creates a boundary. What one is really interested in is, where are the regions of solid hydrate and what are the extents? So the questions from the marine EM, can the CSEM techniques that were just used for de-risking, can they be used to map methane hydrates? And also, if you get resistive regions that are identified by the CSEM, can they be corroborated with other geophysical or geological data? So that was sort of the goal of this. So first of all, just to look at hydrates, they come in all kinds of shapes and sizes, and they could be disseminated, they could be nodular, they could be massive, they could come in veins or veinlets or layers. So all shapes and descriptions. But if you look at the resistivity of the hydrates, they're all really quite resistive, very temperature dependent. Here's the resistivity. Seawater, as we saw before, was about a quarter ohm meter. Freshwater was really resistive. Sediment was conductive. And the hydrate at 0 degrees Celsius is like 20,000 ohm meters. So it's a big resistor. And if we look at gas hydrate saturation as a function of resistivity, you also get this kind of a curve from Archie's law. So large amounts of hydrate saturation are going to give you pretty high resistivities. So what's our survey design? Well, we're going to use basically the same system that we have used before. There's going to be a transmitter that's going to be towed just above the ocean floor. Use a frequency. You can use various frequencies. This one was 5 hertz, and the offset range was 0 to 3 kilometers, so a shorter cable. And then the noise level is on the ocean floor is really low, so 10 to minus 15 volts per amp meter squared. This quantity, this map in here kind of shows the range that you're up against. What we're looking at here is range, so that's the distance from the transmitter, and up here is frequency. There's some parts that have been whited out here, so those are kind of below the noise level. So if you look for the kind of the electric field anomaly from the existence of a layer of 90 meters thick of hydrate that's 2 ohm meters, so that's actually pretty low, right? But you could have low concentration. So the background is 1, you postulate the hydrate, it's at least 2 ohm meters, could be more. But what that does is give you a signal map that looks like this, and at 5 hertz, then you're going to be able to detect this. It's going to be above the noise level from right close range up until about 3 kilometers. And most of the signal that you would get to actually see this thing is coming from this region in here, from like 1,500 meters to about 3,000. So, and again, all this is starting to make some sense, right? So you've got something that is buried, is buried. So you're going to have have a moderately long offset, and you can see things out to a couple of kilometers. So the survey has got a couple of things going for it. So there are ocean bottom receivers that are put onto the bottom. So we've got these Scripps receivers that some of them are actually put on. So the red dots here are actually going to be MT receivers. We'll haven't talked about MT yet, but we'll do that tomorrow. So those are bottom receivers. And then there's going to be a couple of lines of data. There's this one here, which we're going to do a CSEM, we're going to tow that, and then line 2, in which there's another. So there's going to be 2 lines of data that's required. I mentioned when we were talking about DC resistivity that you could plot these as a pseudo-section, right? So that's what's happening here. So you've got a transmitter, okay, and then you've got these receivers, and then each time you've got a, for whatever transmitter you got and whatever receiver you've got, then you plot things at a 45-degree angle, and that gives you a pseudo-section. So depending upon which way you're going and where you are, you'll get a different type of pseudo-section. So here's the pseudo-sections that are associated with this. And it's kind of plotted on the topography, so it's sort of kind of going up and down. And the reds are the low resistivities, and the blues are the high resistive values. So there's some instruments that are towed, or some receivers are towed. There's others that are actually fixed on the ocean floor, and all of those are incorporated. Then for processing, we're going to do an inversion. You need to have a good reference model. So you need to have the topography of the seafloor, and then the conductivity of the water actually changes significantly depending upon the salt concentration and the temperature. So you need to know that, and you put all that together, and that gives you kind of a background resistivity model. You invert that, and you end up with this as an inversion model. It's superimposed. The seismic data is actually superimposed on this. But what you're interested in here are the blue values that are up high, because those are resistive. That goes up to 3 ohmmeters. And you can see that there's a concentration of blue up in here, and maybe a little sort of lighter blue up in there. So those are the areas then that are of particular interest. And you can see that this BSR is kind of coming down through that. So the interpretation here is that these resistors have really kind of identified where the hydrate might be. So this is the BSR that exists. So there's hydrate that's above the BSR, and also hydrate that is below. And in particular here, it seems like there's a lot of hydrate that's sitting above it. So the final interpretation is that you just have a lot more information about the potential existence of hydrate in solid and in gas for how it goes. And in addition to that, there was a seismic tomography that was done on here. And when they did that, they found that there was a low velocity zone here. So that's actually kind of consistent with a lot of gas being there. So you have hydrate that's melted, and there's gas phase, then you'd expect to see that. So there's a lot of consistency here between what was obtained from the seafloor EM experiment, both the reflection and the tomographic aspect of the seismology. So that was it. There is another section, you'll have it in the notes. I don't think we want to go through it at 4:30 in the afternoon. But it really is connected with DC and EM. And let me just make a comment about this. So suppose that I've got some, resistivity structure out here, and I do a DC resistivity. So I'm going to put a current in here, and maybe I'm going to measure some potential someplace, right? Then what we talked about before is that if my current electrode, if my current voltage, suppose it's off, and then I turn it on, and then I leave it on, and I turn it off, and I leave it off. So my current looks like this. If I plot my voltage, then my voltage goes, is 0 when the current's on, and then the moment I turn the current on, then I've got these currents that are going through some body, right? Well, let's do the one that we had before. So we had like an A and a B, got some body here. The moment I turn this current on, then kind of instantaneously I get kind of current that goes through here, and I get these charges that are built up, right? And then I can measure my potential. So that's how we presented the DC resistivity. And when we do that, the voltage that we measure has got some value B, and then we turn the thing off, and it goes like that. So the voltage curve looks like the current, right? And then we had a way of actually calculating the apparent resistivity was equal to, 2 pi times the voltage divided by G or something like that. It's being high. Anyway. In reality, though, that's not quite what happens, right? In reality, when I turn this thing off, okay, we now know, after today, okay, that we've got a grounded dipole here, and there's going to be electromagnetic induction. So rather than having this thing turn, when this thing turns off, rather than the voltage going down like that, I've actually got some EM induction that's going on, and it's going to actually have a signal then that perhaps looks like this. Right? So this part here is EM induction. Okay? And in fact, we could do a whole survey where that's what we do, right? I mean, that's kind of what we've been talking about today. Put a current in, turn it off, measure the fields as a function of time, and then measure these different time channels and invert those, and we got the conductivity. Okay, so that's where we should be today. But when a DC experiment is done, and in particular it's done with respect to looking at something called induced polarization, which we'll talk about on the last day, most of these early data that are actually contaminated with this induction effect are actually thrown away. So what the purpose of this next section is to kind of look at what is standardly done in a DC resistivity experiment, and to say, okay, rather than using this final voltage, okay, as a DC and inverting that, let's actually use some of the time domain information and see if we can't invert to get the electrical conductivity. So it does a comparison of trying to, so in one case, we're just going to do a DC experiment over here, okay, and see what we can get out. In the other case, we're going to kind of do the same experiment. We're going to measure those early times and do the EM induction, invert the EM part, and then see how well we do. So there's kind of like two pieces of information. In doing this particular plot here, we could do, like, just do standard DC and record that voltage and invert that and get the conductivity. Or we could be paying careful attention to what happens when we turn this thing off, and now we've got all these EM induction effects. Could we use that information and recover something?
Yeah.
The section that we've got here kind of takes you a step through and shows that actually we can do a better job in recovering the conductivity by looking at these early time data than we can with just standard DTC. So that's probably enough. I mean, it kind of it kind of merges two things. One is the standard DC resistivity of what's doing, and then what we're now doing as far as looking at early times and inverting them to get conductivity. So you can look at those things. So I think, so what we're going to do then for tomorrow is we're going to start off, we're going to look at, we've now done all the control source stuff that we need to do. So, but we will look at the use of natural sources and bring in something called magnetotellurics. We'll do that in the morning. And then in the afternoon, or maybe even part of the morning, we'll look at the inverse problem, inverse theory problem. That'll be a real change of pace, but it's also something that is generic to everything you do, whether you're in seismic or anything. The same principles will apply. So it's just worthwhile to make sure everybody's on the same page and you have some fundamentals. And then on the Friday, we'll go back and we'll look at ground penetrating radar. We're not going to go into that in great depth, but at least show you kind of the basics of what it is. And you'll see some radargrams and you'll swear that, okay, that's a seismogram, right? Because they look the same. And we'll kind of talk a little bit through that. And then we'll do induced polarization. And then we'll have at least 2 talks. And if there is time, we're going to try to think about a question or two that we would invite you to participate in. And I think that the perfect question in our minds is something like we pose a question and then you're forced to, well, you are invited to select an app, one of the many apps that I've done, and to open that app up and use that to help answer the question. So that's what we're going to try to put together, and we'll at least have a half an hour or something like that on Friday to do that. But I think that would be kind of fun. Okay, so that's it. We will see you tomorrow.